Hello and welcome to Controllers Tech. In the previous video, we explored software timers. We learned how they enable you to create multiple virtual timers and manage them directly from your tasks. In this video, we are going to examine something that directly affects every single task you create in your system, the stack. Let me begin by explaining why understanding the stack is important for your projects. Every FreeRTOS task has its own dedicated stack. When a task uses more stack memory than what was originally allocated to it, the excess data overflows into adjacent memory areas, which corrupts that data and causes unpredictable system crashes. Stack overflows represent one of the most common problems encountered in RTOS-based systems, and they are also among the most difficult issues to find and fix. FreeRTOS provides two helpful tools to assist you in managing and preventing stack problems. The first tool is OS thread get stack space, which allows you to continuously monitor how much stack memory remains available so you can adjust and optimize your stack sizes accordingly. The second tool is the Stack Overflow hook, a special function that detects and catches overflow events while your program is running. Now, there is one important concept you should understand clearly. The free stack value that OS thread get stack space returns is called the high water mark. It represents the minimum amount of free stack that has ever been recorded for that particular task. This value tells you the worst-case scenario for stack usage in your task. Here is something surprising: certain function calls like printf actually use much more stack space than you might initially expect. A single printf call alone can consume around 150 bytes of stack just for its internal buffers, and this happens regardless of how long your text string is. This is precisely why stack sizes should always be determined by actively monitoring your system during the development and testing phase. In this video, we will cover three main topics. First, we will create a monitor task that tracks and records the stack usage of all your other tasks. Second, we will enable stack overflow detection in CubeMX so your system can catch problems automatically. And finally, we will write and implement the Stack Overflow hook function that activates whenever an overflow is detected in your system. Let me start with the project from part 7. I have already loaded it and opened it in the STM32 Cube IDE. The first thing we will do is rename the project to RTOS Part 8. Make sure you check the update reference box, so that the name change is applied at all relevant locations throughout the project. Alright, the renaming is now complete. Next, delete the configuration file and rename the IOC file to Part 8 as well. Now open STM32 CubeMX and load the renamed project. This is basically the same Part 7 project, only renamed to Part 8 for this lesson. You can see that we already have GPIO output pin configured for the LED, and a low power UART configured for the virtual COM port connection. We will use both of these components in our project. There is also an input pin configured for the button. We will not use the button in today's project, but let's keep it in place anyway for potential future use. Now go to the middleware section, and then select FreeRTOS. Here we will make some important changes from the previous project. Open the Include Parameters section. You can see the parameter called UX task get stack high water mark is already enabled by default. We need this parameter because it allows us to monitor the maximum stack usage of each individual task and detect potential stack overflow risks before they cause problems. Since it's already enabled, we don't need to make any additional changes here. In the Tasks and Queues section, you will see the default task that was already created from the previous project. We will rename it to Task 1 and set it to normal priority. The stack size is currently 128 words, which we will keep. Let's also rename the entry function to match. Leave all other settings at their default values and make sure the location is set to dynamic so the task can take memory from the FreeRTOS heap when it needs it. Now we will create a second task. Name it Task 2 with the same normal priority level, but set the stack size to 256 words, which is twice the size of Task 1's stack. Create a third task called Task 3 with normal priority and a stack size of 512 words, which is twice the size of Task 2's stack. Now create a fourth task, which will be our monitor task. Give it a low priority setting so it doesn't interfere with the other tasks while they are running. Since this task will only observe and monitor stack availability in the other tasks, its priority should be the lowest among all tasks. Give it a larger stack size so it can perform all its monitoring operations without any issues. Now we have 4 tasks in total, 3 with normal priority and the monitor task with the lowest priority. The monitor task will measure and report the remaining stack space available in the other 3 tasks. Let me quickly delete the timers that were created in the previous video since we no longer need them for this project. If you go to the FreeRTOS heap usage section, you'll see that we've already exceeded our originally allocated heap space. Go back to the Config Parameters tab and increase the total heap size to around 10 kilobytes to give ourselves enough memory. You can see that the heap error is now gone, so we're good to proceed with the project. That's all we need to configure in CubeMX. Go to the Project Manager tab and click Generate Code to create the new project files. The project has been generated successfully, and in the main file, you can see all 4 different tasks that we configured in CubeMX. Now let's scroll down to the Task Functions section. I need to delete the leftover code from the previous project that we no longer need. We will first observe how much stack space is available when we don't make any changes to these tasks. However, we still need to write the monitor task function, which will retrieve the stack space information from the other 3 tasks. Inside the monitor task function, we will create 3 variables to store the available stack space of the 3 tasks. Next, we will use the function called OSThreadGetStackSpace to retrieve the available space currently remaining in any of the tasks. There is also another related function called OSThreadGetStackSize, which returns the total amount of stack memory that a task has been allocated. However, the OSThreadGetStackSpace function specifically returns only the available space remaining in the task's stack. So we will use the OSThreadGetStackSpace function for our monitoring purpose. The parameter that this function requires is the task handle. We simply need to provide the respective handle of the task we want to monitor. After we fetch the stack space information for all 3 tasks, we will print this information to the serial console so we can view it on our computer. Since we don't want this monitor task to run very frequently and use up processing power, we'll add a delay of 5 seconds before the task prints the information again. That's all we need to do for now. Let's build this project and check for errors. There are no errors in the build, so let me flash it to the board and test it. Open the serial console viewer, and here we will see the results from our monitor task. We need to wait at least 5 seconds for the monitor task to print the first result. Here we have the stack space information from all 3 tasks displayed in bytes. Task 1 has 384 bytes of available stack space, Task 2 has 896 bytes of available stack space, and Task 3 has 1920 bytes of free stack space available. These numbers show us how much room each task has before it would run out of stack memory. Note that we have not written any code inside these tasks yet, so what we're seeing is basically the maximum stack space available for each of these tasks. It's important to understand that these numbers might vary significantly depending on the specific microcontroller you're using, and how your memory is configured. For example, F7 and F1 series boards may have different amounts of total RAM available, which directly affects how much stack space you can safely allocate to each task. That's why it is essential for you to monitor the stack usage according to your specific microcontroller, and the unique requirements of your project, and based on those measurements, you can make informed decisions about how much stack space each task needs, and how much code you can safely write inside it without causing problems. Now let me try to add code that prints information from task 1 on the serial console, and we'll do this every 2 seconds. We will then observe how much stack space is still remaining, and free in task 1 after using the printf function for printing. Here you can see that task 1 is printing data every 2 seconds on the console, and the available stack space has been reduced to only 196 bytes. This means that approximately 188 bytes are being occupied by the printf function, and its internal operations. It's important to note that this is not a fixed number, and might vary depending on which microcontroller you're using. Also, here's something worth remembering: the actual size of the string doesn't matter. Whether you print a single character or a very long string, the memory consumed by the printf function remains almost exactly the same, because printf reserves internal buffers regardless of string length. Now that we know 196 bytes of space are still available in task 1, let me create a local array that is 100 bytes in size and check how much additional memory is consumed by this array. Let's flash this updated project to the board again and observe the results. Here you can see that the free stack space has been reduced further to 92 bytes, which means 104 bytes are now occupied by the array we just created. Even though the array is only 100 bytes, an additional 4 bytes were used for stack frame overhead, and alignment padding that the compiler adds automatically. Now, what happens if we make this array much larger, let's say 200 bytes instead? We already know from our calculations that there isn't enough space available in the task stack to safely handle this much data. But let's try it anyway, and see what happens to the system. You can see that the monitor task is simply printing that the stack space is 0 bytes, which indicates a serious problem. However, notice that the task is still running and continuing to execute its code, and that's happening simply because we're not actively accessing or writing data to that memory location. We only created the array declaration, and without actually performing any read or write operations on that memory area, the rest of the task's code continues to run normally. This situation perfectly highlights the real danger of stack overflow. It doesn't always cause an immediate system fault or crash. Instead, it can silently cause data corruption in adjacent memory areas and create unpredictable behavior throughout your system until the corrupted memory is actually accessed or used by the processor. This is why early detection is so critical. Now we know how to monitor the stack usage effectively. To prevent memory faults and system crashes due to stack overflow, we can implement a stack overflow hook. This hook function gets called automatically when a stack overflow is detected by the system. FreeRTOS provides a special hook function to handle stack overflow detection automatically. If you look in the config parameters section under the hook function related definitions category, you can see there is a feature called check for stack overflow hook, which is disabled by default. There are 2 different options available for detecting stack overflow, option 1 and option 2. Option 1 performs a check to see if the stack pointer has gone out of bounds at the time of every task context switch. This method is faster but may miss overflows that happen between context switches. Option 2 performs additional checks on the stack by using a pattern or marker value placed at the end of the stack. This method is more thorough and can catch overflows more reliably, but it uses slightly more processing power. We will use option 2 for our project because it provides better detection accuracy. If you look at the details below the option selection, you can see that when you select either option 1 or option 2, a function called the application stack overflow hook is automatically created and generated inside the FreeRTOS.c file. The developer needs to write the actual implementation code inside this function to decide what should happen when an overflow is detected. Let's generate this updated project again in CubeMX. Now go back to Cube IDE and open the FreeRTOS.c file, which is located in the source directory of your project. Here you can see the function that was generated by CubeMX. Inside this function, we need to add code to handle the Stack Overflow error appropriately. This function has two parameters provided to us. The first parameter is the task handler of the specific task whose stack has overflowed, and the second parameter is the name of that task as a string. Depending on what operation you want to perform, you can use either the task handle or the task name to identify which task caused the problem. To prevent FreeRTOS from hanging the system or performing unpredictable operations after detecting an overflow, we should call an infinite loop inside this function. This infinite loop prevents the control flow from leaving the function and returning to other tasks, which could cause further corruption or crashes. Let's quickly test what happens now with this Stack Overflow hook in place. The only addition to our system is this Stack Overflow hook function with an infinite loop inside it. Here you can see that nothing is being printed on the console anymore, which tells us that none of the tasks are running their code. This is because the control flow has entered the overflow hook function and then immediately entered the infinite loop, stopping all other task execution. Other than running this infinite loop, we can also print some diagnostic logs that indicate exactly which task caused the stack overflow. For that, I'm going to use the printf function to print the task name on the serial console. Note that the printf function may not work properly in this interrupt-like context, but I want to demonstrate this approach before we move to a more reliable solution. Let's also include the standard I/O header file so we can use printf, and then flash the project to the board again. Here you can see a little bit of data from task 1 got printed normally, but when the overflow occurred, nothing is printing on the console anymore. This happens because printf relies on internal buffering and complex interrupt-driven mechanisms that may not function properly when called from the Stack Overflow hook. In this critical error state, we need to use lower-level UART transmission methods that are more reliable and don't depend on the standard library's buffering system. Let me first declare the UART handler as an external variable so we can access it from the hook function. Now, inside the overflow hook function, we will first to initialize the UART hardware and then reinitialize it back to a known working state. This ensures that the UART is ready to transmit data. Next, we'll prepare the data to be transmitted via UART. For this, I'm going to call the sprintf function to load the error message along with the task name into a character array. Finally, we'll call the HAL-UART transmit function to send this array directly to the computer via the serial connection. Let's build and flash this updated project to the board again. Here you can see the log message is now printed successfully, clearly indicating that there is a stack overflow that was caused by task 1. Let me reset the board again to see the message clearly. Now you can see it clearly states that a stack overflow has been detected in task 1. After this log message is printed, the control entered the infinite loop, and therefore the other tasks are not running anymore. Now let me quickly reduce the stack memory being occupied by task 1 back to a safe level, and flash the project again to the board. Now you can see the logs are printing normally without any issues or warnings. This means the overflow hook function is not being called anymore, which indicates that task 1 is operating within its allocated stack space. So I hope you now understand how to monitor task stack usage in FreeRTOS, and how to handle stack overflow situations. We saw how to use the OS_thread_get_stack_space function to monitor the remaining stack space in your tasks. We also enabled the stack overflow detection feature in CubeMX, and implemented the hook function to catch stack overflow errors, and log them to the serial console using direct UART transmission. That is it for this video. You can download the project from the article linked in the description of this video. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.